Hey, welcome back. Just a quick tool room tip here. Let's say you're running a milling machine and you have no tool preset or not a wrencher probe or a tool probe in the machine, and you want to touch off your end mill to a very precise distance to your work so you know where you are in C height. The very classic way of doing it is to use cigarette paper. Be extremely careful because that's a good way to crack a cutter. You just drop the cutter down until the cigarette paper kind of grabs under the cutter. I don't like this method a lot because you're getting awfully close to the surface with a very, very expensive tool, and it's extremely hard to tell once you're there. And on top, you do not really know how much you squish into the cigarette paper. So now the cigarette paper is kind of grabbing, and when I check the thickness of the cigarette paper with a micrometer, it's kind of in the range of 30 to 40 microns usually, depending on what you buy. So now I would punch in 0.03 or 0.04 millimeters into the DRO, probably a little bit less than what I measured here because I squished into the paper. This gives you a very good starting point already. It's very cheap, but as I said, it's extremely dangerous because you have the end mill or your cutter extremely close to the surface, and if you over travel, you chip the cutting edges, and this is a 60 euro T-slot cutter, so I don't want to crack it. What I prefer is to use a hard gauge. Either a gauge block or a gauge pin, or even better, because it doesn't cost anything, because you most likely have it, the shank of an end mill. End mill shanks are relatively precisely ground to size. This one is literally like 1 micron under size. And gauge blocks are near and precise. I'm not a big fan of using gauge blocks because it's kind of sacrificial, because it will scratch and wear if you do this. This will give you an extremely precise distance of your cutter to the work surface. I find this to be often more, this is way more precise than one of these things, Heimer 3D probe. To touching off C height with these is way less accurate than using a hard gauge. So the idea is you could do it two ways. You can drop the cutter far enough so the gauge block or the pin drops under the cutter, and then you just raise incrementally and you try if the gauge block still fits under. Once it doesn't fit anymore, you have to play a little bit back and forth until you find the perfect spot. Not my preferred method. What I prefer is to drop the cutter below the surface of my gauge that I'm using, so it doesn't fit under. And then I'm dropping the axis very slowly, like in extremely small increments. There we go. That's sliding under it. And now I'm exactly 10 millimeters off the C height. Well, exactly. There is still a tolerance, but it's close enough for most work. If you need an extremely precise depth that you're working to, you have to measure your feature that you're cutting and adjust accordingly. But this will get you 99.9% of the way. But as I said, I don't like to use a gauge block. My preference is something round. And why? Well, I will show you. So when I drop the C-axis of the mill, and I very carefully push the pin against the cutter so I don't damage the cutting edge. I can feel, due to the round nature of the pin, that it's also getting closer to my cutter. And that way I get a very good feedback of what is going on. See, now I'm the diameter of the pin away from my top surface. Let's compare these three methods with actual measurements. Okay, let's start with the gauge block as a reference. Let's crank the C-axis to some value, zero it out so we do not know where we are. Okay, let's touch off with the gauge block. And I'm using the C-axis drop-down method. I'm getting close. The cutter is already running up the chamfer of the gauge block here. And you see on the DRO that I'm dropping down very small increments, like 5 micron at a time. That's just a nudge on the hand wheel. That's a technical term, by the way. So here we are, slides under. And this means that I'm now 10 millimeters away from the surface. Now let's use a 6 millimeter carbide pin. I'm dropping down so I'm below the pin. Also, it's nice that with a pin you can span features in a part. So for example, in this case I can span over the central bore in this part. And now I'm just doing the same deal again. Let's do it from this side. Maybe you can see a little bit more. And I'm just dropping down the C-axis very slowly. And I can see that the pin moves towards the cutter at the same time because I'm putting slight pressure on here with my thumb. And I'm almost there. One last nudge, and there we are. Well, it's within 10 micron. Let's do a repeat measurement. There we go. Okay, this is repeating rather well. And just for fun, let's try the cigarette paper. I'm cranking extremely close just by eyeballing the gap between the part and the cutter, so I don't have to approach extremely far. Then I slide the cigarette paper in here. Oh, well, yeah. It's free sliding. And I start to drop the cutter very slowly until the paper starts to grab. And I would say that's grabbing. That's not coming out on its own. And when we look at the DRO, we get 0.037 millimeters. And the paper micrometer at 0.04. So it's kind of in the same realm. But as I said, if I remove the paper, we are awfully close to the part. So I don't like this method a lot because it can end up very expensive cracking cutters. So while on the topic of C height, we also have the lathe. Here it's not called C height. Here it would be the y-axis. But tool height on the lathe, of course, is also important, and there are a lot of different ways of setting it. And most of the time I have a very, very simplistic way of approaching it. Well, that's also the way I learned to set it. Let me show you. you have your tool here in the lathe. You just change the tool in the tool holder, and now it's far from being on center. A lot of people will tell you that you can just take a facing cut and adjust by the tool approaching the center, and that's very true. You have to be a little bit careful because some tools like this aluminum insert will react a little bit salty if you drive it a lot over or under center height, and react by chipping, which is expensive if it's like a €7 insert. So I try to not do that with more fragile inserts, and I will show you a very fragile tool later. So I try not to do that. So one way of setting the tool height that we were taught in apprenticeship, and that really works quite well if you have nothing but a caliper. You have a piece of stock in the chuck. It can be unmachined or machined. It's not really critical. This happens to be already machined in the setup. So you just take the diameter 30.74, divide that by 2, and you end up with 15.37, and you set your calipers to that dimension. Well, 10 microns off, but we're not chasing microns here with this method. And now you have then you just use the depth rod here off the top of the piece of stock in the chuck, and you have a very good basic idea how to set your tool height. You just move the tool up until you notice that you touch the depth rod of the caliper. You can also do this without the clamp and actually measure it, but I prefer to preset the caliper and use it as a hard gauge. This is not ultra precise, but it will get you very close and doesn't require anything. Oh, and don't forget to lock your height adjustment screw off your tool post. So that's one method, but we can't always do that. Another option, if you don't want to use the calipers off the stock, is to use a hard gauge with the center height of the machine off the cross slide. This only really works if you have a machine that has a ground or machined cross slide. On very old machines, you often have this rear end of the cross slide still as a rough casting, and this method does not work. Then you have to go, for example, off the machine bed. So on this machine it's very easy. The center height off the cross slide top surface to the center of the spindle is exactly 70 millimeters. So I took an old gauge block, a 70 millimeter gauge block, and I super glued a second gauge block on top of it. And this gives me a very, very nice height gauge. I can put on the cross slide here, and I can just slide it over my tool and use it as a hard gauge this way. And I can raise and lower the tool until it doesn't fit under the inverted surface here anymore. And at that point I know, well, I drop it a tiny amount, then the gauge fits again over the cutting edge. And this is an extremely sensitive way of doing it. And you get really, really close. And if you're careful, you're not damaging standard cutting tools. If you're a little bit ham-fisted or you drank too much coffee, this might not be the ideal method. You can chip and insert this way. You also can just go with the center height and just take a mirror so you get a nice look from the side and compare the height of the gauge block to the cutting edge. Then it's without contacting the actual cutting edge. a small dental mirror is really, really useful for this. Or you can get your head in from this side and look at the cutting edge and the gauge block and compare their height with a magnifier. That's also a method that's working very well, but I can't show it because, well, the camera is in the way. Here is the height gauge in action. You can see that the gauge block moves nicely with a lot of clearance underneath the gauge block, and it just slowly raises the tool until it makes contact with the cutting tool or the insert. Now I'm there. Now it doesn't slide over the cutting tool anymore, and I just back off the height adjuster screw a tiny amount, lock it again, and now the gauge block moves over it again. I can repeat that a few times with smaller and smaller height adjustment increments on the tool post, but usually 1 or 2 tries gets you extremely close. This also works for weirder tools like a diamond burnisher that has literally just a diamond ball on its end, and you need to get it on center height somehow. And here we can just move the gauge block up very close, not touching the diamond tip because it's kind of delicate, and we can just use a magnifier to visually set the ball shape to the height of the gauge block. It would be a good idea, I think, to grind a little bit of a knife edge onto this gauge block to create a really sharp edge. The factory chamfering on this gauge block is really not helping here very much. Or here, another example. This is a inserted grooving tool or parting tool. We can either use the gauge block to compare the height, or we can use this side of the stack up to actually use it as a hard gauge for the tool height. Works really well and very simple. Now we have a problem. There are tools that we absolutely cannot gauge this way, and that's diamond tooling. Of course, that's an that's not something that everyone has to deal with. In fact, not very many people in general use monocrystalline diamond. This is literally a chunk of diamond brazed onto a carbide insert carrier, then ground and lapped into shape. This needs to be very much on center height to work properly, especially when you take facing cuts. So how do you set this? Optically would be nice because you don't want to use a hard gauge on the cutting edge. This would be extremely bad and very expensive, since such an insert will run you several hundred euros or dollars. So what would be our options? Cue the surface gauge. So we have, this is getting a little bit convoluted on here on a crosslight, but it will work. So I have a surface gauge, standard surface gauge. You can use something like a Noga base on a 1-2-3 block, so it can slide on the compound too. And I use my gauge to zero out the dial test indicator. And with dial test indicator zeroed out, it's just a matter of moving over to our diamond tool, and we don't go with the tip of the dial test indicator over the front of the tool because we will chip the cutting edge. We'll come in from the trailing edge of the diamond and move on to its land surface, and we can see our actual height. And now we can very precisely actually measure our tool height. Most tool posts will change their height when you tighten them. So apparently we are like 60 microns under zero, but when I tighten the tool post, it's more like 20 microns. So we'll undo height adjustment lock here, And we'll just raise it by 20 microns. Just like this. And and there we go. Sometimes it will change again once you tighten the jam nut on this style of tool post, but then you just have to adjust and take the change from jamming up the height adjuster into account and adjust accordingly. That's our diamond tool set to center height, and now we carefully move the indicator tip off the trailing edge of the diamond, not over the cutting edge. That would be bad. So we move it up to the back. And we can just for fun compare, for example, to this tool that we just set with the hard gauge. And you have to move it a little bit around to find the high spot. But this will give you a very exact reading, and with the hard gauge we set the tool to 20 microns under center height. Well, for a grooving tool that's more than adequate. So the indicator method takes, of course, longer. It's slower, but it's a very precise way of doing things. You know what's going on. To figure out your center height, you turn a piece of stock in the chuck to a certain diameter, and you crank your cross slide under the work. And then you use gauge blocks between the cross slide and the work, and you figure out this distance. You add half the diameter of your turned stock, and then you know your exact dimension from the cross slide to the center of the spindle. And you just write down that dimension, and you know it until you rebuild the lathe. Then it might change, then you have to measure it again. But that dimension, in my case 70 millimeters, is very useful. Since I mentioned the MKD tool, the monocrystalline diamond tool, you might be wondering, why is Stefan using such a horrendous expensive tool on such a mediocre lathe? Since this is not an air bearing or diamond turning lathe, this is just a regular tool room lathe with fairly rugged tapered roller bearings in the spindle, not even angular contact. Well, the results the diamond yield are still very, very good. I'm making some scientific apparatus at the moment out of plexiglass PMMA, and the material as it came off the saw looks like this. This is what you would expect from a circular saw cut on PMMA. I wrapped the material in PET tape so I can grab it in a chuck without damaging it, and the PET tape is more consistent in thickness than the original thin wrapping the round stock came in. That's the reason why the green color. But that's of course not the point. The point is this finish off the saw. I can get a fairly good finish in PMMA with a good carbide insert, but this is what I'm looking for. let's have something behind it so this is the finish that I get straight off the lathe with the MKD insert, taking a facing cut in a depth of cut of about 50 microns to 100 microns. Dry, just with air. I know that there are people who say, well, just use oil when you machine plexiglass and it will become optically clear. Yeah, that's true. Until you wipe off the oil and decrease the part, then it will go back to a matte finish. The oil just changes the refraction of the surface. It's not really doing anything magical to the plexiglass. The diamond, on the other hand, is so sharp that it leaves a clear surface. There is still the topography. When you look very closely, there are surface imperfections. That's just bearing noise and belt noise on the lathe and slideway noise. that translate directly into the surface. But the noise is machined with such a high microscopic surface finish that it doesn't show up when you just glance at it. When you know what to look for, this is not a optical element surface in any means, but it looks really good for most applications. So that's why I'm using diamond. Also, I'm making some laser mirrors out of aluminum that also require a diamond turned finish. That's the main reason why I have the diamond, but as I was making these PMMA parts, I figured, well, I could just use the diamond here too and save me some handwork. Okay, over at the lathe, PMMA clamped in a 6th jaw, protected with the PET tape. I have a DCMT07 insert for aluminium, polished and ground, with a 0.2 millimeter radius. Going to take a 1 millimeter facing cut, a 0.1 millimeter facing cut, and then I change to the diamond and take a about 50 micron facing cut, all at a feed of 60 microns per revolution. And I'm going to use compressed air to control the chips. Okay, that's the 1 millimeter facing cut, and in all honesty, that's already not bad. Let's take a 0.1 millimeter cut, just to see if we get a difference. I would say it's a little bit better, and there is some moisture in my compressed air, obviously. Now it's time to change to the diamond. This is a diamond insert from Contour Diamond. It's extremely expensive, but works really, really well. I know that the two techniques showed, one setting the C height on the milling machine and the other one being setting tool height on the lathe, are kind of inherent different topics, but in my mind they kind of go together for some reason, and I hope you get an idea of how to solve things, despite it being a rather basic skill and technique. But still, there's many ways of doing things, and there isn't a really right or wrong, and it's not black and white. It's all gray scales of techniques, and these things I showed work for me very well and usually don't create problems. So thank you all for watching, and I'll be back.